All right, welcome everybody. Today we're going to talk about lesson number 47, and we're basically going to go back through a couple of the lessons that we talked about so far, revisit them a little bit, add a couple things, and then talk about a few new things that will kind of bridge us to the upcoming lessons. So I'm going to call this Revisiting the Law of Sines and Other Trig Relationships. It seems a little bit disjointed, a bunch of different topics, but I promise there is a reason for it. So first, to remind you of the law of sines and the law of cosines. So as a reminder, you're going to use these formulas when you are solving oblique triangles. Again, just to reiterate, if it is a right triangle, you should continue to use SOHCAHTOA. But if it is an oblique triangle, which means not right, you can use the law of sines or the law of cosines to go ahead and find all the missing sides, all the missing angles, and of course, solving to 3 decimal places each time. The main thing I want to remind you of before we start is that you need to be back in degree mode in your calculator. So you might want to double check that depending on where you were after last night's homework. You're going to want to make sure that you're in degree mode. So speaking of solving oblique triangles, remember that you're supposed to use the law of sines in certain cases and then the law of cosines in other cases. So as a reminder, you're supposed to use the law of sines when you either have angle, angle, side, angle, or side, side angle. And I had put a star next to this one when I first showed you, and I'm going to put a star there again. That is what's called the ambiguous case of the law of sines, and we're actually going to talk more about that today. Speaking of the law of sines, there technically are 2 different versions. They're just reciprocals of each other. Remember, the general relationship says that if you take the sine of any angle over the side across from it, it is equal to the sine of any other angle divided by the side across from that, and you can set it up for all 3 sides. Remember, you're only ever going to do 2 of them at once. So you would, for example, set up a ratio here, or you would set up a ratio here. You would never do all 3 at the same time. It is recommended that you use the version on the left side if you're trying to find missing angles, and it's recommended you use the version on the right side if you're trying to find missing sides. The truth is, it really doesn't matter which version you use. If you just have one version you prefer and use it all the time, it works just fine. But again, if you're looking for a bit of a shortcut, you can feel free to go ahead and take that advice. Just kind of showing you a quick example. So here on the left, you notice that you are given 42 degrees, 50 degrees, and 11. So you're going to go ahead and solve for the side across from the 42, which would be x. So you're going to use the law of sines version on the right there, which says if you do x divided by the sine of the angle across from it, it equals 11 divided by the sine of the angle across from that. You would then go ahead and cross multiply. Do not plug anything into your calculator until the final step. Once you get x equals, very carefully plug that into your calculator, keeping in mind that you might need to use extra parentheses, especially if it opens them for you. You have to close them, and you get that x is equal to approximately 9.608. Remember, regardless of what examples I have for you here or what values are given to you, you should always round your answers to 3 decimal places unless stated otherwise. Again, remember, a good way to check that you are doing it correctly is that in the end, the largest angle should be across from the longest side, the smallest angle should be across from the shortest side, and then the middle should be in the middle. That's an example of the law of sines solving for a missing side, and then over on the right is an example solving for the missing angle. So again, notice they've used the other version where the signs are on top, but it really doesn't matter either way. There is a slight algebraic advantage to using one version versus the other, but in the end, it will work just fine all the time. So the sine of an angle x over the side across from it is equal to the sine of 42 over the side across from that. Again, cross multiply. Go ahead and take the inverse sine. Remember, to get the angle, you have to take the inverse sine. My recommendation is that you not actually round this value. I would just actually leave it as whatever this quantity is. That's just a good way to ensure that you don't lose any decimal places. And then even though it has only rounded this answer here to 2 places, you're going to round to 3. It's just a matter of how many examples I could find on the internet. So the problem with this ambiguous case, why we have to kind of revisit today, is because of cases like this, where you're solving for a missing angle. And notice that in this example, you have a side, and an angle. So these are the kinds of problems that could give you an issue, and we're going to see exactly why in a minute. Before we do that, let me just remind you about the law of cosines. So the law of cosines, remember, you're supposed to use when you have side, angle, side, or side, side, side. Technically, there are actually 6 different versions of the law of cosines, 3 for solving for the various side lengths, ABC, and then 3 solving for the missing angle measurements, ABC. So again, it is recommended you use the left side where the cosine is isolated for finding missing angles, and using the right side where the squared is isolated when you're solving sides. But again, really either version works either time, so it's kind of up to you. Notice that here in the first example, you have side, angle, side, and you're trying to solve for, in this case, x. So they're going to go ahead and just make the replacement. Remember, you're just kind of following the pattern. So to find a missing side length, which in this case, they're using as the c squared version, but they're calling it x squared, it would be one of the other side squared plus the other side squared, always minus 2 times those 2 sides, times the cosine of the angle that matches. Remember that you are not going to plug any of that in until the final step. And because it's x squared, you're going to go ahead and take the square root, and you would get x is equal to approximately 7.632. Again, we have examples of this back in our notes, but I just wanted to kind of give you a refresher without making you write every single thing down. Over on the right-hand side, notice that you have side, side, side. So if you have side, 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 you're going to go ahead and potentially use the version that isolates the angle. Remember, the general pattern of the angle is one side squared plus the other side squared minus the matching angle squared divided by 2 times the other 2 sides. Again, once you do those calculations, in order to actually find the missing angle, you're going to have to do the inverse cosine. When you do the inverse cosine, you're going to go ahead and get the angle, which is 113.741 degrees. So again, I just wanted to refresh your memory since it's been honestly like 2 weeks since we did this lesson. You might want to go back and look at the ones that we did to see the step-by-step process. I just wanted to find some stuff online where I could refresh you without having to show you every single step. So why are we coming back to this now when we already did it? Well, we actually know a little bit more information about the sine and cosine now. And so that's going to be enough for us to figure out what happens with the ambiguous case of the law of sines. Just to be clear, there are no issues with the law of cosines. The law of cosines will always work perfectly and always give you the right answer. And again, my personal recommendation, if you start a problem using the law of cosines, I would just finish it using the law of cosines, so then you don't have to worry about the ambiguous case of the law of sines. But again, that's up to you. So what is it that we now know that's going to help us? Well, it turns out we actually need to consider the graphs. So let's go ahead and do so. So what I have for you there is a little unit circle on the left-hand side with those quadrantal values. Then I have the sine graph and the cosine graph, which you may or may not have seen before. And we're going to talk about where they came from. So when it comes to the domain of the sine and the cosine, you're taking the sine or the cosine of an angle. So the sine of 30, the sine of 150, the sine of negative 30, the sine of 1,000. You're taking the sine or cosine of some angle. Because of the fact that you can take the sine or cosine of anything, big or small, positive or negative, that means that the domain is all real numbers. That essentially means you can go around the circle as many times as you want in either direction. And from left to right, the graph is going to go on and on forever. When it comes to the range of each function, because of the fact that the length of the radius on the unit circle is only 1, the largest that the length of the radius can be if it's pointing in the positive direction is positive 1, and the longest it can be if it's pointing in the negative direction can be negative 1. So the range of the sine and cosine is negative 1 to 1. Both functions are called what we say periodic because they repeat in a repetitive manner, meaning that it starts to repeat after a given set of x's. Those x's are determined to be the period, and it's how long it takes to complete one full cycle. And both the sine and the cosine have a period of 2 pi, which you should note means 1 revolution, so 1 trip completely around the circle. So everything that's kind of highlighted there and bolded, those are some new vocab words. We're going to talk so much more about graphing in the upcoming weeks, but now we just want a little bit to start. And again, we need that for our law of sines and cosines. So let me just show you a little bit more precisely how we take these values from the left-hand side of the unit circle and go ahead and actually create these graphs. So starting with the sine wave, we're going to go ahead and start at 0. Remember that sines are y values. So at 0 degrees or 0 radians, you're going to go ahead and look at the ordered pair. The sines are, of course, the y values. So the y value at 0 is 0, which is why this is the point 0, 0. Then if you were to go up to pi over 2 radians, the sine is the y value, which would be 1. Over here to pi, the y value is 0. 3 pi over 2, the y value is -1, and then back to 2 pi, you're back to 0. So this here is considered to be one full wave of the sine, one period, as it were. It's 2 pi because that's how long it takes to go through one complete up-down motion. You can see by the fact that over here on the left, between -2 pi and 0, the fact that it looks the same, that's what it means to be periodic. It keeps repeating. The whole reason why 0 has the same value as 2 pi is because they are coterminal. So again, any values that are coterminal have to have the same value of the sine. And that's, again, part of why this is periodic. Something else we want to consider, now we know that there are a lot of values between 0 and pi over 2, a lot of sine values that we could have graphed, and you can continue to use those if needed. The main thing we want to focus on is the positivity and the negativity. Remember that for sines, all students take calculus, mean that the sign should be positive in quadrant 1 and quadrant 2. So notice that here's quadrant 1, here's quadrant 2, and notice that the sign is positive in both of those locations. Conversely, the sign, the y values, are supposed to be negative in quadrants 3 and 4, which is exactly what the graph shows us here. Let me erase all that and now go back and do a similar study in order to find the cosine. So remember, when it comes to the cosines, these are actually x values. So as you go around the circle, you're going to scoop up the x values. So starting at 0, the x value is 1, which is why you start up at the top. Pi over 2, the x value is 0. -1 at pi. 0 at 3 pi over 2. And then back to 1 for 2 pi. So again, this is considered to be one complete wave of the cosine. It again has a period of 2 pi because it needs one full revolution to make the complete all the way down and then all the way up revolution. Again, you'll notice that this is going to repeat as well. So for both the sine and the cosine, you need 2 pi, one revolution, to make the complete graph, but they look slightly different. They do have similarities. The difference is that each graph is shifted by pi over 2, and that's because there's only a limited number of values here on the unit circle. They differ by pi over 2 in terms of the x's and the y's, and again, we'll talk much more about that when we're graphing. What we want to consider here is the positivity and negativity. So remember, all students take calculus. Cosines are x's, which means they're supposed to be positive on the right side, which would be quadrant 1 and quadrant 4. And then x's are supposed to be negative in quadrants 2 and 3. So that's why the positivity and the negativity is slightly different than the sine wave. So here's why this matters in terms of the law of sine. So think about solving an oblique triangle. If you're talking about solving a triangle, any triangle has angle sum 180 degrees. So you cannot have any answers that are larger than 180 for any single angle, or else you wouldn't actually have a triangle. So if you're thinking of that in terms of the unit circle, that means you can only consider the top half. So you can only consider places where the angle is between 0 and 180, which means you can only consider the top half of the circle. There are two different circumstances that can happen. If you're solving using the law of sines, you can get that the sine equals a positive, or that's it. If you think about the cosine, you can get the cosine equals a positive, or you can get the cosine equals a negative. And here's why. If you're solving for the sine, you're only able to consider this part of the graph, which means you're only able to get a sine value that is positive. If you were to get any negative, that would be not possible. And because of the fact that you're getting a positive, it means you could potentially be getting answers in quadrant 1 or quadrant 2. So that just means you have more than one potential answer. When it comes to the cosine, however, cosines are positive in quadrant 1 only, and cosines are negative in quadrant 2 only. So no matter what, the law of cosines is going to give you the correct answer, but the law of sines, you have to double check. Regardless of whether it's the law of sines or the law of cosines, please note that the range has to be from -1 to 1. So setting all that up, let's go ahead and talk about the law of sines ambiguous case. So only the law of sines. We have already seen that if you have two angles and one side length opposite them, that determines a unique triangle. Again, when it comes to law of sines, angle, angle, side, and angle, side, angle don't give you any issue. The one that we do have to watch out for is the ambiguous case, side, side, angle. And it turns out that when you do the ambiguous case, there are three possible things that can happen. So thing number one is you might have a triangle that's no solution, which means no triangle exists given those measurements. The second thing that could happen is that there's one triangle that exists and you simply find it. The second thing that exists is that there could be two different triangles, and then you have to find both. So what you have here is all 6 different things that might happen. I'm not saying you have to actually memorize all 6 of these cases. In fact, I don't think that you should. But basically, when you have a triangle and you're given side A, side B, and angle A, and then again, if you remember back from the proof of when we did the law of sines, we set the ratio that H is equal to B sine of A. So basically, here are the 3 things that can happen. You could potentially draw a triangle where angle A is acute and the length of A is too short to complete the distance, which means that no triangle will exist. There can also be a similar scenario if A is obtuse. Basically, you have an A that's too short to complete it. So those are the cases where there are no solutions. Then you have circumstances where there's just one solution. So one of them is when it's a right triangle, which again means use SOHCAHTOA. The other is where you have an acute angle. You have the value of A being greater than or equal to B, and that gives you one triangle, no problem. And then again, you can have an obtuse angle where A is distinctly greater than B, and again, that's going to give you just one triangle. The problem happens when you have an acute angle A, and you have an A that is between H and B, you could potentially have 2 different solutions. So one of those solutions would be this green triangle here, and the other solution would be this red triangle here. So that's the one we have to watch out for. It only occurs in the side-side angle circumstance. And the reason why we have to look for it is because, again, sines are positive in quadrants 1 and 2. Because any reference angle for quadrant 1 and 2 for certain values would be the same, we have to consider both possibilities. So there's a lot of different ways that I could teach you this. Here is my recommendation. Try to solve the problem as if there is a solution. If it turns out that there's no solution, you won't find it and the problem is over. If you find one solution, go back and check to see if there's a second one. So to make life a little bit easier, I'm going to tell you up front which one it is. So here's an example of a side-side angle single solution case. So you're going to go ahead and be given some information, and you're going to go ahead and draw an oblique triangle. Again, it doesn't really matter if it's to scale. So let's go ahead and label it ABC. Across from angle A would be side A, which would be 12. Across from angle B would be side B, and then 31 degrees. So hopefully you are able to understand why this is angle side side. So we're going to start by using the law of sines, but we're going to have to go ahead and double check to see if there is potentially a second solution. So whenever you're given a side-side angle situation, there's only ever going to be one thing that you can solve for. And in this case, the only thing you have enough information to solve for would be angle B. So you're going to go ahead and set up that 12 over the sine of 31 would be equal to 5 over the sine of b. Cross multiply and then divide. So the sine of b will be equal to 5 sine of 31 over 12. Once you get to here, you're going to go ahead and solve for angle B by doing the inverse. So the inverse sine of 5 sine 31 divided by 12. Again, if you plug that into your calculator exactly as it appears in degree mode, you should go ahead and get that B is equal to 12.392 degrees. Then you're going to continue solving for the rest of the measurements. I don't think I need to show you all of that, but if you were going to solve for angle C, you would add 31 to 12.392. You would subtract it from 180, and you would get 136.608. That would be the second angle C. And then if you did the law of sines to solve for little c, you would get 16.006. Again, I think that you could do those calculations. That's not where the law of the ambiguous case comes in. That's what we already did. So remember, solving a triangle means find all the missing sides and all the missing angles. So you have solved that triangle just like normal, assuming that there's just one solution. Because of the fact that it is a side-side angle, you are going to ask yourself, is there a second triangle? Here's how you determine if there's a second triangle. Whatever the first angle you found is, which would be angle B, you're going to find the supplement. So you're going to do 180 minus 12.392, and that's going to give you 167.608 degrees. So what that means is that if there was a second triangle, then angle B would be equal to 167.608 degrees. Then you have to check if you take that potential second angle and you add it to the original angle, could you have a triangle? So if you add 167.608 plus 31, you're going to get 198.608 degrees, which is larger than 180, which means it's too big, which means no second triangle exists. So that's it, game over. Your only answers are the ones that are highlighted in yellow. So again, let me just kind of go back from the top here. You only even have to consider this when you have law of sines, side-side angle. You're going to go ahead and solve it like normal. And if it works, you're going to get one solution. Then go back. Whatever angle you found to start, you're going to take the supplement. Then you're going to check it with the original angle to determine whether it's greater than 180 or less than 180. If it's greater than 180, then it's too big and no second triangle exists. If it's smaller than 180, there is a second triangle and you would go ahead and solve. So that did not happen here in this case, but it will happen again shortly. So that is your one solution case. Now let's consider side-side angle, the no solution case. So again, you're going to go ahead and start by drawing a triangle. Because of the fact that I know what's going to happen, I'm going to have you draw the triangle just so you can visualize it. So let's go ahead and consider a triangle A, B, C. And here's what is actually happening. So angle A is 60 degrees. Side B is 14. And then they're telling you that side A is equal to 4. Turns out that if you had a large angle of 60 degrees and you had a B of 14, that A, being a length of 4, would be too short. It would not be able to actually complete the triangle. Now, instead of you having to draw it and actually check it, let's assume that we didn't know that it didn't work and we were going to just try and see if we could solve this. So if we were going to try to see if we could just solve this, again, we'd be solving for angle B. So we would go ahead and set up our law of sines, which would be that 4 over the sine of 60 is equal to 14 over the sine of B. Cross multiply and divide, and you would get that the sine of B is equal to 14 sine of 60 over 4. If you try to take the inverse sine of 14 sine of 60 over 4, your calculator is going to say domain error. And here's why. If you calculate 14 sine of 60 over 4, that is actually equal to 3.031. One of the things we went over earlier, let me scroll back here, is that the range of the sine and the cosine has to be between -1 and 1. So the fact that you got a value of the sine that is larger than 1, that is not possible, which means there is no angle B. And if there is no angle B, then there's no triangle altogether, which means this is a no solution. No triangle, given these measurements, can possibly exist. So again, consider what's happening so far. So again, both of these are side-side angle, and at first glance, perhaps they didn't look any different. So again, my advice would be try to solve the problem as if there's one solution. If there is one solution, finish it and then see if there's a second one. If you don't get a solution like we did in number 2, then there clearly isn't one solution, which means there can't be 2. So what would it mean if there was 2 solutions? So again, here is the original information. You're going to go ahead and start by drawing a triangle. And again, it doesn't matter where you put A, B, and C, and it doesn't really even matter if your problem is necessarily to scale. So 58, 4.5, and B equals 5. Again, the only thing we can solve for when it's side-side angle, there's only going to be one angle that you can go for. So in this case, we're looking for angle B again. So we're going to set up that 4.5 over the sine of 58 would be equal to 5 over the sine of B. Cross multiply and divide, and you're going to get the sine of B is equal to 5 sine of 58 divided by 4.5. If you then go ahead and do the inverse sine of 5 sine of 58 over 4.5, that is going to tell you that angle B is equal to 70.437 degrees. So because you got an answer, there is at least one triangle. Then, because you know angle A and because you know angle B, you can then subtract them from 180, and that would give you angle C, which would be 51.563 degrees. Then you would set up your law of sines again. You would solve for little c, which would be 4.156. So again, here in red and yellow, these are your answers for one triangle. There is at least one solution given these measurements. What you need to do now is you need to check, is there a second triangle? If there is a second triangle, you're going to find the supplement of the first angle that you found, which was B. So you're going to do 180 minus 70.437. If you do that, you're going to get 109.563 degrees. Then you need to check by taking that potential second angle, adding it to the original angle, which was 58, and seeing what that's equal to. 109.563 plus 58, you're going to get 167.563. Notice that that is less than 180. So a second triangle does exist. And now you have to find it. So whatever this supplement was, that means that's the second potential triangle. So if this is the second potential triangle, that means that B would have to be obtuse, which means here's the second potential triangle, ABC. The values that were originally given are still true. So A would still be 58, little b would still be 5, little a would still be 4.5, but now B would be 109.563. So if there is a second triangle where angle B would be 109.563, you now have to finish solving this triangle. So you would have to do 180 minus 58 minus 109.563. That means your second triangle would have an angle C of 12.437. And then if you solve for little c, that would be equal to 1.143. So more so than anything else, these are just a little bit annoying. Solving for all the missing sides and all the missing angles using the law of sines isn't a big deal. But yeah, having to do it twice is fairly obnoxious. But again, you only have to do it when you are given the ambiguous case. You only ever have to check whatever that first angle is. You have to consider the supplement. And again, the reason why is because sines are positive in quadrants 1 and 2. So how do we know which angle it is? Well, we don't, which is why we have to consider both. Now that we've reviewed all the different ways to solve for the missing sides and missing angles, just a brief reminder of triangle area formulas. We already did the formula on the left. Remember, given any two consecutive sides and the angle between them, you can find the area by doing 1/2 the product of those two sides times the sine of the angle between them. And then here is another new formula. It looks like Heron's, but it's actually Hero's formula. Here's what it says. If you're given the three sides of a triangle, ABC, you can calculate the area by taking the square root of S times S minus A times S minus B times S minus C, where S is equal to A plus B plus C over 2. And just so you know, that is half the perimeter, which is called the semi-perimeter, which is why it's the letter S. Remember, semi means half. And actually, this is a very easy formula to use, and it's very easy to calculate the area. So in number 4, find the area of a triangle with side lengths 5, 8, and 9. You can draw it if you want to, but the truth is you don't really even need to. So you're going to go ahead and start by finding the semi-perimeter, which means you're going to add 5 plus 8 plus 9 divided by 2. So that looks like 13 plus 9 is 22 divided by 2. So the semi-perimeter is 11, which means the area is going to be equal to the square root of S, which is 11, times 11 minus 5, times 11 minus 8, times 11 minus 9. You can calculate those parentheses if you want to, or you can just plug it in your calculator exactly like such. And it turns out that it's 19.900. And again, it should be squared. So square inches, square feet. In this case, we're just going to call it square units because of the fact that it's area. So just a reminder that these two formulas, while great and helpful, they are only true for area. So make sure that you don't use them for anything other than area.